I'm doing the demos for those who couldn't come to the review. I handed out a sheet and I'm going to send it to you as a PDF, and then you can just follow along and I'll quickly hit the high points of each demo. We had a cardboard, we hung it down, say from some hole, and we knew that when it would stop swinging right away, that a vertical hole then would go, a vertical line would go from that hole through the center of mass. Draw it. Then do it again from another hole. Draw that vertical line. They must intersect at the center of mass. And then I can check that that really was a center mass by putting a nail through it and just trying to swing around that, and it would just swing freely because there's zero torque due to gravity when you're going through the center of mass. The period is infinite. Next demo. When we threw a baseball back and forth, if somebody in the middle threw a ball straight up such that he started exactly when the other ball was thrown, and if it went right up to the top and just went to the same height as the other, then in fact they would intersect and it would end up that we had identical y trajectory, identical time, identical height, and the y, the vertical part of the trajectories of the two would be exactly the same. If they intersect, the times are the same all the way through the trajectory. That's like the monkey one. When we shot at a monkey, if there was no gravity, we just aim at it straight away. If there is gravity, when we shoot, we ask that the monkey drop at exactly the same time. If so, our y, our vertical coordinate, will be identical when we get in line, and we will have to hit the monkey. That's because the y part of the trajectories for both are identical. In the next demo, all we had to do was take the top brick and make sure that its center of mass was just on the edge of the next guy. And then the center of mass of the two of those guys was just on the edge of the next. And then the center of mass of those three was just vertically over the edge of the next guy. And ditto for the four perched on the fifth brick. And of course, we analyzed that in homework. But the neat thing was the roll of the center of mass and making sure that it was right on the edge and not any farther so that it wouldn't tip over. In the next demo, if we had a marble or a ball or something coming and hitting another one that was at rest, an elastic, then we knew that if their masses were the same, we'd get this famous 90 degrees between. If this guy is bigger, it plows through and the angle then between them is smaller. If this guy is lighter, well, if it was very light, it could bounce backwards and the angle is bigger than 90 degrees. And so we have these ranges corresponding to the differences in the masses. You'll remember that when we had a tape and we pulled it out, just a measuring tape, and then we let it go, it was moving linearly. But when it hit, it turned into a rotating tape measure. Well, I got angular momentum there. It must be that I have angular momentum associated with this motion, even though it was linear. We had a wheel with two lights on it, and we could see where instantaneously the contact point with the floor had zero velocity instantaneously. And then if you had some velocity v for the center, the top would have twice the v. All consistent with just a rotation around the contact point. We had the old demo of comparing a whole bunch of rolling objects going down a ramp. We found that it was independent of the mass because the mass really cancels out between kinetic energy and potential energy. It was independent of R because R just came in with multiplied by omega R, and for a given V, then if R got bigger, well, omega would just get smaller. But it did depend upon beta, the relative moment of inertia. That was because beta represents rotational kinetic energy, and the bigger the rotational kinetic energy, the less energy you've got for translational motion. So as beta went up, the velocity went down. We had a bunch of springs. When we looked at an oscillating spring and we compared it to two identical springs, with the same mass at the bottom, this guy would oscillate less. It has, of course, the frequency is less because the effective spring constant is half. Conversely, when I put them in parallel rather, this was a series, this one would oscillate faster because its effective spring constant was twice this guy. We showed a damping example when we just showed how it damped on the side of a glass tube. And we had a driven, so this one we could kind of look at the transient, and then here we could look at the steady state by driving it with an external motor, and we saw that when we matched the frequency of the driving motor, I could get a resonance. I could get this thing to really oscillate up and down fast with big amplitudes. That was on resonance, and we saw that in our solutions. When we ran along with two erasers, if we could apply a constant force and it was big enough, then there would be enough normal force here and therefore enough friction to stop this from sliding down. That's hard to do because we couldn't maintain it very long running along on the floor. But we could maintain a normal force that was big enough by just going in a circle. One way I like to say is the centrifugal force on this thing, if omega is big enough, is constant. I get a constant normal and I get a constant friction so that the inside guy, I have to hold the outside guy, will stay without sliding as we go in a circle without us having to run and faster in this direction because we have acceleration inward.